Assalamu alaikum everyone. Last time we discussed and obtained the equivalent circuit diagram for synchronous generator. So we said we have three phase windings on the stator side, which in each phase could be modeled is the resistor with in series with the synchronous reactance and the internal generated voltage. So where the internal generated voltage was basically related to the machine constant, the flux in the machine, and the speed of the machine, rotating speed of the rotor. And the synchronous reactance basically consists of reactance due to the armature reaction and the reactance, the self reactance of the armature coils, and the resistance is simply the resistance of the winding. So today our goal is to discuss more about the behavior of the synchronous generator when we are connecting the synchronous generator to the different loads, and we also want to discuss how can we find out the power generated by the synchronous generator, okay, and then we'll finally discuss the stand-alone mode of the synchronous generator. So let's get started. We are going to start by discussing the phasor diagram of the synchronous generator. So what you see on the left side of your screen is what we call the per phase equivalent circuit of the synchronous generator. So per phase equivalent circuit means we are only looking at the one winding and the load connected to it. And throughout this discussion, our primary assumption would be that our generator is connected to all the three phases are connected to the same load, which we call the balanced load, right? So our target so we will not be discussing the cases where all three loads are different, which is called the unbalanced load, which is beyond the scope of this course. So we are assuming all three phases are connected to the same load, and in that case we can easily work on only single phase circuit equivalent side, which we call the per phase equivalent circuit. So if we have a per phase equivalent circuit and we connect a load, any load over here, which is the per phase load, equivalent per phase load seen by a single phase winding, so then we can easily write the equation for KVL for the internal generated voltage, that the internal generated voltage will be equal to V phase plus IA times RA plus JXS. And this equation is basically the phasor equation because all the quantities are the phasor quantities. It means in order to understand that we need to draw the vectors to see how do these quantities vary as we change the load. Either we change the amount of the load or we change the nature of the load. So first we'll consider let's change the nature of the load. So that vector diagrams are basically called the phasor diagram. We already have seen those in our transformer discussions. So let's assume कि हमारे पास we have this phase voltage, that is we assume कि the phase our reference vector जिसके with respect to we are defining the angles or the phase the voltage. So it means this is our V5. So let's now bring in the load current. So this is our load current which is in phase. So the first case that we are considering right now is the resistive load. So we are saying that we have a resistive load connected to the output of the synchronous generator, and we want to see how does the internal generated how does the net phasor diagram look like, and we'll draw the conclusions from there. So we have a current flowing in the winding which is in phase with the V phase because it's a resistive load, and now we can apply this equation to get our the EA. So it means our IARA component will be in phase with the V phase because RA doesn't have any angle associated with it, and the JXS will be perpendicular. So this is IARA component, and this is JXS times IA component. So that will be perpendicular to the to our V phase. It means so now we can add all these vectors. So you can see I have placed by the head to tail rule, and then you can get the final vector which is EA. So this is your EA vector. So this is primarily what we call the phasor diagram for the resistive load, and we can see how all these vectors stand with respect to each other. So let's now see how will the phasor diagram will look like for the case of the inductive load and for the case of the capacitive load. It's very simple. So as you can see the same phasor diagram for the resistive load. So if you have an inductive load, we have a current that is lagging behind the V phase by this is the phase angle or the power factor angle. So let's suppose this is our theta. So only thing that will be changed in this case is that our this vector will now be again aligned with our phase current times IARA for the inductive load, and it will have a JXS component perpendicular to the IA perpendicular to the IARA. So it means you have a this component added into our system. So this is basically this vector is basically IA times RA plus JXS. So this is a net vector for all these for these two vectors. So now you can combine those and you will have a phasor diagram for the inductive load. And similarly you can do the same things for the capacitive load. In capacitive load, a current leads the voltage. So it means your current now will be in phase with your IARA component will be now in phase with the IA. Then you will add the IA access component which will be 90 degree to the IARA because of the J term, and then you can add the vectors and you will have the phasor diagram for the capacitive load. Okay, so these are the basic phasor diagrams. So now we want to delve a little bit into the deeper and to study the more behavior of the circuit, the behavior of this simple circuit, okay, for the different cases. Okay, so in order to study more about the behavior, we are going to impose some conditions here to study how does the different loads compare. So let's assume that we have the same phasor diagram of the resistive load here, which is that this is V phase, and you have a EA component and IARA component and JXS component. So before we compare this phasor diagram with the different with the different nature of the load, so this is for the resistive load, we need to ensure certain conditions that those are imposed for this study. So the condition number first is that the speed of prime mover is fixed. Speed of prime mover is fixed. Okay. So the speed at which the prime mover is rotating the rotor of the generator. So yeah, so it means that your omega is fixed. Secondly, the field current is fixed. So we are fixing the field current as well. So field current is fixed. So it means your phi is the magnetic flux is fixed in your equation. So the result of these two assumptions is that your internal generated voltage, the magnitude of the internal generated voltage is fixed. So it means कि magnitude of internal generated voltage depends upon the flux and omega. Since both are fixed, it means the magnitude cannot vary in the machine. Okay, so that is fixed. That's what we are going to impose in our phasor diagram. So third thing that we want to assume is that our load. So our magnitude of the load current is fixed. So magnitude. So essentially, when we want to compare, we want to see कि we want to ensure कि we only vary the nature of the load and we do not change the other things. So we want to keep the magnitude of load current loads same, magnitude of load current same. So it means we are only varying the phase angle of our load current. So it means कि IA is same, only the power factor angle is varied, or it means कि the nature of the load is being varied. So these are primary assumptions that we are going to impose. How we are going to impose these, we'll shortly see. So first of all, we say कि हमारे पास our load current is fixed. It means कि this is our load current, this is IA. So it means कि the load current cannot cross the circle boundary. It should remain inside the circle. Okay, so it means कि if we are considering the inductive load, so inductive load will look like this one with the phase shift of angle theta. Okay, so now if we want to compare the resistive load and the inductive load, and if you see the phasor, the components, the resistive component and the reactive components, so the reactive components corresponding to this load current will be shown in the dashed part. So that will be the phasor diagram. So now we need to impose. So we have imposed the one condition here, so which is the IA is fixed. So now we need to impose these two conditions here, which is our EA cannot vary. It means that EA's magnitude cannot vary. So it means that EA should lie on this circle. It should not cross this circle point. Okay, so that is the magnitude of the EA. Okay, so it means that our vector needs to shift leftwards. And the consequence of that is that because your EA cannot vary and your load current is fixed, it means that your terminal voltage is going to decrease. So you can see the terminal voltage, the phase voltage highlighted in yellow, that your phase voltage is basically decreasing as we change the nature of the load in case of the inductive case. Okay, so for a given field current, so that's a summary of the discussion. For the given field current and the magnitude of the load, the terminal voltage is lower for the lagging loads and higher for the leading loads. So if you repeat the same exercise, when you move this vector in this direction, and then you will see the terminal voltage increases for the phase voltage, increases for the capacitive loads or for leading loads. So that's the conclusion here. So if we extend the same phasor diagram and we do some approximation, then we can actually get a very important equations for the power and torque in the synchronous generator. So let's see those. Okay, how can we do that? So first of all, that we have the same phasor vector. So again, let me write the equation here, that your internal generated voltage is basically equal to V phi plus IA RA plus JXS. So this is our basic equation, and we say that let's suppose this component is very small, which is the IARA component. So that is usually true mostly because your resistive the resistance of the armature winding is very small as compared to the synchronous reactance. So it means we can safely ignore this part, and we can say that EA will be approximately equal to the V phase plus J times IAXS. Okay, so if this is a V phase vector, and then we have let's suppose the inductive load. So let's suppose we have an inductive load with an angle, the phase angle of the angle theta. So it means we can now again construct the phasor diagram, and using the same equation that we have a phi phase plus JIAXS, we can now add IAXS like this, because it's going to be at 90 degrees to the phase grad. So then we have this component, which is the IAXS component, okay, and then we can add those two vectors to get our EA part. So let's do some resolution of these vectors and along the V phase and perpendicular to the V phase. So we break the IAXS vector into the two parts. So one part is along the V phase, and the second part is perpendicular to the V phase. So now an interesting thing that you can see here is that this angle, which is the angle here theta, you can prove from the geometry that this angle is same as this angle. So this is basically because of the the theorem in the geometry that the perpendicular the angles to the angles between two lines and the angles between the lines which are perpendicular to the same lines are equal. So it means you can see that this line is perpendicular to this line, and this line is perpendicular to this line. It means the whatever the angle theta is there, it's going to be the same angle in between those two lines as well. So it means this angle is the theta, and let's assume that this angle is equal to sigma. So it means this component, which is the y component, that can be written as so now we have the two triangles here. So let's name these points. So this is O, this is A, this is B and C. So one triangle is OA and B triangle, and the second triangle is the ABC triangle. Okay, so we have the two triangles here. And so if we see that the y component, the one that is highlighted here, so that component can be written in so if we see from the triangle ABC, that is basically your IA XS cos theta. And if we see from the triangle OAB, that is going to be, because it's the same, it means that will be EA sine sigma. So we have this property that EA sine sigma is equal to IA XS cos theta. Okay, so let's see what's the power in case of a three phase circuits. We know that the power is equal to 3 times V phase and I phase, which is in this case is IA cos theta. Okay, so it means we can now substitute this IA cos theta term from this expression into this equation. So we can write that IA cos theta is equal to EA sine sigma divided by XS. So it means that you can easily write that P, the power output of the machine, will be equal to 3 times V phase times EA sine sigma divided by XS. This is very important equation, so this is the power output, and also the power, this is P out, and also the P conversion, because essentially when we assume that RA is equal to 0, it means P out is equal to P conversion. Sigma is known as the torque angle of the machine. Okay, so it means so we can say the torque angle, because the torque depends upon this angle. So we can easily find out that the torque is equal to power divided by the speed of the machine, So it means the torque will be equal to 3 V phase EA sine sigma divided by the speed times xs. Okay, so that's the equation for the torque. The torque angle is basically is what governs the maximum power of the synchronous generator, the power that the generator can generate. So it means if we increase the torque angle, you will have a more power output in this case. So if in the ideal scenario, when the sigma is equal to 90 degree, then in that case we'll have a maximum power. So the max P max. So the maximum power will be when maximum power will be when sigma is equal to 90 degree, which will be 3V phase IA divided by xs. So this will be when sigma is equal to 90 degree, and that is called the static stability of the machine. So you cannot have more power than this expression. Okay. So and usually if we see this practical generators, आपके पास full load पे usually the machine operates at the angles at the torque angles of the around 20 degrees. Okay. So that's these are very important equations. We'll use those equations to study and to conclude more about the behaviors of especially in the case of the synchronous motors. Okay, so keep those equations in mind. So you see on the slide is the summary of what we just discussed, and that we have the power flow diagram on the left. We see that if we have the I square R losses, if we ignore the I square R, if we ignore the resistance, it means these are not there. It means the power conversion is equal to power output, and in that case your P will be equal to 3V phase EA sine sigma. Sigma is the torque angle of the machine. Okay. So let's now summarize our discussion. So we have discussed a number of things, number of behaviors when we were going through the derivations. We also discussed their physical meanings. So in this section we are going to summarize what we have learned so far, and we'll add more we will relax some conditions जो हमने पहले impose की थी. So let's suppose we have a generator that is supplying to a particular load. So this type of operation of a synchronous generator is called the synchronous generator operating standalone, right? So the interesting thing about the synchronous generator is that the behavior of the synchronous generator depends upon the internal characteristics or internal characteristic like the field current and the speed of the synchronous generator, but also how it is connected to other synchronous generators or connected to the same grid. Okay. So right now we are only targeting the standalone mode. We are not covering the parallel operation of the synchronous generator, but so keep one thing in mind, that when you are using the synchronous generator in parallel mode, then the behaviors are a little bit complicated than this one. So let's now focus only on the standalone mode. That you have a synchronous generator that is just simply supplying the power to the load. So the question that we mainly want to answer here is that what happens if we increase the load. Okay. So that's a main question that we want to target here. And last slides that we had the three assumptions. So in which case, so first assumption number one was omega is fixed. It means the prime mover is rotating the shaft at a constant speed. And secondly, the field current is fixed. So we said that the field current is fixed as well. And so it means that it means that EA is fixed. The magnitude of EA is fixed. And the third condition was load is fixed. So now we are going to relax that condition. So load is fixed. So that was so now load is not fixed, load is variable. Okay. So we want to study we know how does the motor behaves when vary the nature of the load when we impose the conditions. So now the third condition is that we also want to know, okay, when the load is varying, it means our load current is varying, what will be the effect on the behavior of the machine. For the last case, our conclusion was for resistive and inductive load, the terminal voltage decreases as you increase the phase angle in the inductive side, and the terminal voltage increases if you increase the phase angle towards the leading side. Okay, so that was it. So now we want to increase the load on the this was our construct last time, that we have an inductive load, and now we want to relax this circle, and we want to say, okay, for example, we increase the IA in this guy. So when we say that we increase the IA, we are keeping the phase angle same, we are just increasing the magnitude of the current, and this is our V phase, this is our EA and IA, RA and JIA axis. So so now it should be pretty much clear that when you increase the IA, you will be basically increasing the length of these two vectors. Okay, so it means that these two vectors in vector scalar we have a magnitude of the IA involved. It means that these vectors will get increased and combined with the condition that our EA cannot increase beyond the circle, it means that our V phase is going to further decrease. Okay, so the general conclusion here is that if you increase the load, if you increase the lagging load, you will decrease the terminal voltage significantly. So if we increase the lagging load, it means we are increasing the plus Q, which is the reactive power of the lagging load. It means your V phase will decrease significantly, and if we increase the leading load, it means minus Q, your V phase will increase significantly, and if you increase the resistive load, it means if you increase the resistive load, in that case V phase will still decrease, but not so significantly as compared to the inductive load. But still there will be a decrease in the V phase, as we saw in the phasor diagram of the resistive load as well. So in चीज़ों की measure करना, we already have studied how can we measure or capture those behaviors. So these behaviors are basically captured by the quantity voltage regulation of the machine. So we know that the voltage regulation is basically the voltage at no load minus voltage at full load divided by voltage at full load times 100. It means that when we have a lagging load, which is the lagging power factor, it means in that case your voltage regulation will be greater than 0, and also for the unity power factor, voltage regulation will also be greater than 0, because in both cases when you will be increasing the load, your terminal voltage will be decreasing. It means these quantities will be decreasing. It means this will always be greater than V full load, and that's why you have a positive voltage regulation. But for the leading power factor, you have voltage regulation of less than 0, because when you increase the full load for the capacitive load, the leading load, it will increase the terminal voltage. So that's basically your summary of the synchronous generator when we increase the load current. Okay, so let's summarize what we have done so far. Learn so far the synchronous generator operating is standalone. The real and reactive power supplied by the generator depends upon the load. That's obvious in the case of the synchronous generator, and the frequency of the electric power will depend upon the mechanical speed of the prime mover, which is basically set by the governor. So governor is basically the control system. So governor is basically the control system for the prime mover, which controls the speed of the prime mover. Okay, so whatever the set point, it means the speed of the prime mover is, that basically decides the operating frequency of the synchronous generator. Okay, and for any given reactive power, the field current controls the generator's terminal voltage. Okay, so as of course we know that the EA is equal to K phi omega. It means K, when you increase the field current, you'll increase the EA in this figure. So in all these figures you'll increase the EA. It means that you'll be increasing this circle, the diameter of the circle, the radius of the circle. It means K, you are also increasing the terminal voltage, is from this equation that V terminal is equal to EA minus IA RA plus JXS. Okay, so if you increase this EA by increasing the field current, you can also control the terminal voltage. That we also discussed in the last our Q&A session. So I think we'll end here, and if you have any questions on this, you'll let me know in the chat box, and we'll discuss in our Q&A session. Thank you very much for your attention. Allah Hafiz.